All right, welcome everyone. Welcome to webinar 4 in our series of IoT webinars. I think we've got a really interesting conversation for you today. Looking back on some of our IoT webinars we've done, we've talked a little bit about the simplicity of implementing IoT in your application. We've also talked a little bit about some of the HR, some of the personnel sides about having engineers on planes going around and servicing machines, right? And then we've also covered the financial side of it, right? Building an ROI to make sure it makes sense for your company. So today, we've actually got quite a few guests on the call. We have myself, Adam Fain, electronic controls and IoT integration specialist with Applied Fluid Power. I've been with Applied Fluid Power now for about 6 years, but I've been in the industry for about 17 years. And then we've got Viraj here from Applied as well, and then two other of our partners. So Viraj, why don't you go ahead and introduce yourself?
Yep. Hi, everyone. I'm Viraj Vora. I'm with Applied since over 1.5 years. Been here as an electronics control engineer. I help in most of system integration and recently been part of IoT initiative and the electrification initiative that we have started recently.
Awesome. Thanks, Viraj. Carl?
Hi, I'm Carl Hayes. I work with Elevate. I am on the IoT side of the application, and I've been working with Elevate for about 4 years and been responsible for deployments through Applied, and looking forward to this discussion.
Awesome. Thanks, Carl. Lewis?
Yeah, hi, I'm Luis Mernigo. I'm a VP of Business Development for TwinThread. TwinThread is a AI-enabled, scalable digital twin platform. Today, I'm going to talk about how we apply all the advanced technologies, including digital twin hierarchies, AI capabilities, and automated workflows to help customers get to autonomous services on the equipment management and fleet side of things. So looking forward to the discussion as well.
Awesome. Appreciate you all being here today. So we have a QR link if you're interested. We've got an area here where you can capture more of our IoT webinars that we've already presented. Here again, we've kind of gone through the simplicity of integrating IoT on your current machine. Here again, the HR side of it, and then the ROI side. So if you scan this QR link that you see on the screen here, it should take your phone right to that link. So today, I think we're going to cover quite a few topics. We're going to hopefully not try to boil the ocean here, but this is a really exciting part about IoT. After we get past the initial connection and being able to stream data, after we start to understand some of the business requirements that you have, but what do we really actually do with that data? How do we really take that data and grow that and make that a huge, very valuable part of your business operation? So we're going to talk about new product development cycle. We're going to talk about what IoT 3.0 is and how that's involved with new product development. And we're also going to give you some use case examples, and then we'll actually hear from Carl and Luis as well on some examples from their platforms as well. So we're going to cover a lot today, but hang with us. And here again, this meeting is recorded. So if there are questions that you have later, or if there's something that we're covering here that we kind of go over quickly, just go ahead and watch the recording later. All right, Carl, so you got a really good example here. I guess maybe tell us what this is.
Yeah, I thought it would be a good idea to just kind of take a walk back in history, back to 1936, when Alan Turing, widely considered some of the father of computers and potentially in machine learning, was tasked with a problem of cracking the German Enigma. And what Enigma would do is basically encrypt the German messages so that the Allied forces were not able to tap into them and get advanced plans on what the Germans were doing, such as bombing, ship movements, troop movements. And Alan came up with the Turing machine. And essentially what that did is it went through very rapidly to try to decipher each of the letters within the code. And so this would be one of the examples of using automation or a machine to try to take a very large problem and ultimately get a result that you're looking for, which is to decipher each of these reports. And so in order to do that, he needed something to contextualize the code that he was working for and essentially establish meaning. So one of the first problems with these kinds of examples is that the machine just kept churning and churning and churning because it didn't have anything to really contextualize what the message was until they found in the daily weather report that the Germans would transmit Heil Hitler. And so with Heil Hitler, that created basically a key indicator that they could start with each day so they could decipher at least those letters. And then it allowed the machine to continue to work and ultimately decipher the rest of the message. And it was a turning point for the war. So we thought this would be a good way to show that not only has, this kind of thinking been around for a long time, going on almost 90 years, but that he was dealing with the same kinds of issues that you're going to see that we are dealing with today.
Excellent. So yeah, there was a ton of information coming through that nobody really understood to begin with. Excellent. No, that's a good point.
So catching up to today, or into the future, data comes in a raw form, much like these encrypted messages that the Allies were dealing with. And that data has a time series, so it comes at a specific time, and it has an event as well. So certain things happen within that time series. So with Mr. Turing, you're looking at a weather report. So on the event, they needed to decipher that. The data was essentially being plugged in to try to figure out other reports from that information that they were getting. So they were aggregating that data, um, looking at it, trying to make meaning of it, and ultimately derive knowledge. So IoT today is at a point where we are gaining knowledge from this data. So that means that we're understanding when machines are in need of fixing or need of uh, changing fluids. And we're gaining a certain level of knowledge from the information, just like Alan did with the Turing machine. But now it's time to really go to the next phase, which is deriving real wisdom or knowledge that we can use or automate. And so machine learning has come in, and artificial intelligence to, in a sense, supervise and automate some of this information that we've been collecting and managing up to this point. And so moving forward, we're going to talk a little bit about how that impacts the new development cycle. So how we can do a better job of creating new things. We're going to talk a little bit about how we can monitor existing fleets and get a better insight as to how it's performing, prevent catastrophic failures. And then ultimately, the idea is that we get to focus on what we do best and have the software, in a sense, help us do a better job of managing the fleet, just like Alan Turing used basically machines to crack the German code so that he could focus on making decisions about helping where to send the troops, how to deal with the ships, and that's ultimately where we'd like to get to.
Well, Carl, that's a really good point too, because I think, in my experience with IoT, one of the struggles that I've seen is customers struggling to really understand what does that data mean. We can stream, and I've said this in every webinar, we can stream engine RPM and we can stream engine coolant temps, but what does that really mean for the machine, right? So maybe let me ask you this. So where does like a maintenance module as part of Elevate, where does that come into play? Like, is that IoT 1.0, 2.0, or is really that 3.0? I guess where would you categorize that?
Yeah, so the maintenance module, just to kind of break it down, is a way to automate over your fleet system when a machine needs to be maintained. So let's say every machine has a 500-hour interval, and I'm using IoT to gather that information and then understand or gain knowledge from when's the right time to take care of that machine. So that's clearly a 2.0 use case. And at the top, as we can see, we ultimately, the business outcome we're looking for is that it impacts the bottom line. So it's either helping us make money, save money, or optimize our productivity. So just like with the Turing machine, ultimately the outcome they were looking for was to win the war, not to break code. So there was a real objective, an overall strategic objective that the machine and the technology was used to affect. Just like with IoT and machine learning, it's not that we want to fix or maintain a particular machine. It's that when we keep our our machines in good health, we optimize their productivity, we reduce unplanned failures, we predict catastrophic failures, what ultimately drives our profitability for the organization.
Interesting. Okay.
With all the information that you shared, I just feel that data is our new oil. Without data, we are not being able to move forward, or we are going to be very much dependent on data as we move forward. So I want to just bring in my perspective of where we're going to fit in and where we're going to extract the data. For example, any new product development that we look into, it begins with an idea, be it because there's a need in the market, or if we want to improve an existing design. So we'll look into design process and then see what are the different parameters, where do we need to consider those, and then build a prototype, test it, be it endurance test, life cycle test, and try to match whatever we had in theory. If it works, just fine. But that's all just in the prototype phase, and we're not going to eventually get actual results until we launch it and the customers start using it. So once it's in the field, that's where I think we can gather all the data and utilize the power of fleet and analyze data from different systems in different situations located in different places.
So Raj, that's probably also a good point too. I mean, you and I as both engineers, I think we've ran into the case before where, we take information off of one machine, it's a prototype, and of course, if we're around the machine, right, we're probably driving it a little bit different than what the actual operator does. But what you're actually proposing here is not just getting data off that one machine that's out in the field working, but you're actually saying getting it off of the fleet with, 99% of the operators being real world operators operating this, right?
Yeah, in that way, we'll get different situations. For example, just take an example of a car. I might be a rash driver, but someone else might not be a rash driver. So how I operate a car would be much different than how someone else operates, and how things go hand in hand. Like my engine might heat up a lot because of my conditions, and someone might just be fine with it. So having that visibility across all the across the fleet is going to help us a lot improve and make a design better.
That's a really good point. Thank you.
What do you think about continuous product development, Viraj, in terms of a typical development cycle? You design, you implement, and you deploy, but with what you're talking about, you might be able to make continuous enhancements to the machine over its life cycle.
Yes, absolutely. So once everything is deployed, we still have the capability to analyze the data and see over a period of time how it is changing. There are, for example, over a period of 1 year, due to different temperatures, there might be a lot of parameters that would change. For example, your oil that you're using in the system might heat up and the system might behave differently. And having all the data will help you understand what all fixes I need to make so that it's weatherproof. You can run it across the year in any condition, in any geographical location. So it helps drive a lot of continuous improvement projects based on key performance indicators that you're going to constantly keep monitoring based on the data that you have.
Awesome. Good question, Carl. So I think what I'd like to do is I want to give you an example, as it relates to the fluid power industry, as it relates to applied fluid power. Here's one that, excuse me, here's kind of one that Viraj and I are probably very familiar with, that we've seen many times. Traditional load sense type system, right? So you've got, in this case here, a multiple stack directional control valve, proportional control. And oftentimes when we work with customers on this, it's going to, there's going to be some sort of Excel sheet or design parameter sheet, and we're trying to size pressures and flows for each of the functions. We're trying to understand how often does that system or does that function run as compared to other functions, right? So we're gathering all this information, but I think for the most part, a fair amount of them is really kind of an estimated guess, or it's based off of current, machine designs where maybe one engineer is looking and saying, okay, we think that this function runs 1500 psi, or this function runs 2000 psi, for example. So we're making very educated guesses, but up until now, I don't think we have a ton of data that we're really looking at when we're making those design tweaks. So I want to give one example here. In this case here, we've got 3 functions here that we're analyzing. Function 1, 3000 psi at 10. You can see what function 2 is, but function 3, this is one I run into all the time. Oftentimes in a load sense capable directional valve, we think that by reducing the pressure setting or the max pressure out of that set or out of that section, that we're actually saving energy. Now in this case here, by actually running IoT on this one machine, what we found was the pump still has to run at the 3000 psi based on the other functions running. So in essence, we were actually creating additional restriction in that system. So I know there's a lot on the slide here. I don't expect you to go through all this, but I just kind of put some simple calculations together based on the actual IoT data now that we know that the machine's actually running this way. And what we realized was, oh, we are actually burning energy in this case here. And as you guys can see here, I put in here $3 per gallon for gas. I mean, I don't think any one of us has paid $3 a gallon for gas for quite a while. It's probably quite a bit more than that now. I know mine was just yesterday, but this is real factual information that I think would be really hard to extract off of just a design criteria sheet. So in this case here, maybe what would have been better is to size that function 3 for 3000 psi, but maybe only 5 gallons a minute, and actually change the displacement of the actuator so you're still running at that optimal pressure, just at a lower flow. But here again, I think these are some of the insights that we don't see until we get to like what Raj said is, we're actually seeing data off of the field. How does that fleet really perform? How does it really work out in the field?
Yeah, I totally agree. And just adding one point here. Before we added the IoT on the system, we never knew that the system is inefficient. We were just able to perform all the tasks as per the requirement. Customer was happy, we were happy. But only when we implemented our IoT solution, we came to know, oh, there's a lot of scope here. We can save a lot of money. And if we apply this across the fleet, eventually it turns out to be like a lot of money for the company, a lot of savings, and making the system efficient.
So, I'll also highlight here too, here again, having IoT on this machine, we were able to extract this information out of the fleet, but this did take some serious time to be able to pull this information down, be able to really understand that and detect that this was an issue. But I think, here again, what we want to cover today is that we have better tools to do that once you're ready to kind of move past that initial data collection side. And so I wanted to give Carl, you said you actually had a really good idea on how to take some of that information and make it very simple to understand of where we should focus our engineering efforts.
Yeah, and I appreciate that thought, because really we are actually focused on a business outcome. We want to make sure that this makes sense for the business managers. And in the engineering side, oftentimes that means trying to keep things simple, trying to make things not require a ton of analysis, and in a sense automate and help us make better business decisions. So for example, we came up with the operating equipment effectiveness KPI. And really that's just meant to tell us on a machine how much it shows up for work, when it's showing up for work, how much of that time it actually spends working, and how much time it spends getting to and from point A to point B. And so with that one simple KPI, we can take this IoT data and we can essentially automate that calculation so that a business manager has to simply look at his fleet and he can very quickly tell which machines are optimum and which are not. In a sense, we call them good and bad citizens. So we want to determine how to make our bad citizens more productive and how to encourage and maintain the good citizens in the state that they're in.
I feel there's a
So
lot of value here. And in the past, we have had such requests from customers, and it takes a lot of time for each individual customer to implement each individual parameter and track it and then give them results. But here what I see is you've already developed certain aspects of it and automated it so that we do not have to do as engineers a lot of work to implement what you've already done, and it just adds on top of it.
that's right. And we even can continue to build on this layer by adding the machine learning and artificial intelligence to it to be able to do some of the correlations maybe that we weren't before. So we can take a key performance indicator and we can look at maintenance and see if there's a relationship between the two, which we all pretty much suspect that neglected machines are not going to perform as well. But with Lewis coming in and bringing his technology on top, which he's going to cover here, he can show you how that actually all pulls together.
Yeah. Thanks, Carl. So today I was going to build on what Carl and Viraj have presented in terms of capturing data, making sense of it, applying KPIs, and talk about how we can then enable the journey to autonomous services for fleets and equipment service providers by essentially leveraging an end-to-end AI-enabled digital twin platform. And we know that different industrial companies find themselves at different stages of the journey. And it's really important that we meet our customers where they are in this journey and help them to automatically supervise, adjust, and optimize the performance of their entire fleet, not just a subset of that fleet or individual pieces of equipment. Yeah, so TwinThread is a platform, an end-to-end platform that leverages all of your existing data and data infrastructure. In the case of Elevate, they're a partner that provides the IoT platform for us as the foundation for our digital twin creation and the operationalization of actions across the fleet to drive improvements. The architecture really enables a virtual picture of your operations, and in the case of factories, also within facilities, based on the development of AI-driven solutions that can rapidly be operationalized and rolled out across the fleet of assets. So really, value creation is really important here, and Carl made a point in his slide about focusing on business cases and business cases that have really important economic value associated to them. And that's where the value of all these technologies comes in. Value creation is accelerated through our pre-built AI applications that include both anomaly detection and predictive models. And essentially, these applications are targeted at specific challenges and opportunities that are most commonly found among either manufacturers or field equipment providers. And these pre-built applications include process-centric use cases such as quality, throughput, energy efficiency, and uptime, as well as asset-centric use cases that include uptime, asset reliability, asset life, in some cases throughput as well. So our platform delivers both process and asset-centric solutions that scale and enable your subject matter experts to operationalize actions that will improve the efficiency of the fleet, as well as drive and help enable autonomous services and create new business opportunities from that. The platform is extremely flexible and it allows our customers to leverage their existing investments, their IoT platforms as well, to drive innovation across the entire organization.
As an engineer, I feel there's someone who's listening to us. Like we've always seen that, be it a weather report, you're always told that be careful in the next day or two, you might have a tornado, and you keep you plan yourself and are prepared so that you can tackle it better. And now you're saying that we can do the same thing on systems. You know that what is gonna go bad or what is not behaving as usual, and there are anomalies, and you will let us know as engineers that you need to focus your time in this particular section and go there and fix something before it breaks out.
Yeah, certainly. It's the process of automatically identifying variability across thousands and thousands of parameters and intelligently learning from what high-level operations looks like and maintaining that level through ideal conditions, ideal set points, and indicating any situations where variability is higher than normal, and flagging that as an opportunity to create workflows that can be deployed automatically across the fleet and ensure that you're always running at an optimal level. So that not only increases efficiencies, but also gets ahead of any catastrophic failures or costly failures across the fleet from a component, whether we're dealing with individual components or the entire machine itself.
So Lewis, I think it's important to kind of note here too. So what you're saying is you don't necessarily need to have an engineer go through and create all of these rules for you. They don't have to say pressure can't exceed this or variation can't exceed this. Your platform is starting to extract that information for them. They're not having to write 500 different
Correct.
rules based on previous catastrophic events.
Correct. And they also do not have to build data science models or the IT infrastructure and the applications that support the flexibility of the platform, the ability to operationalize actions, and the ability to scale, which is really, really important. Those three things are absolutely critical to be able to deliver value from IoT, digital twins, and artificial intelligence.
That's excellent.
So this is an example of a customer that we're currently working with, where we've delivered a virtual center of operations for them. So TwinThread's complete platform that has all of the AI-driven applications built into it really delivers exceptional ROI. And it's because we can scale, it's because we can operationalize. We take all that rich data also from IoT platforms like Elevate and apply AI capabilities and apply workflows that prevent issues and also optimize performance of assets from a single platform. And in this particular customer example, we prioritize the reliability and the performance of critical power equipment across 450 data centers. And there are a couple key points I want to highlight regarding this particular example. We did this and we enabled 2 technicians and 1 engineer to optimize the performance of these critical power equipment assets across the 450 data centers. So it's 3 subject matter experts optimizing all those assets. And we had remote operations of hundreds of sites that is really only possible with an accurate representation of the physical assets and the data context. And that's where the digital twin comes in. There's a lot of definitions of the digital twin out there. And from our perspective, a digital twin is the digital representation of the physical asset, but it is the mechanism for automatically contextualizing, preparing, organizing, and making sense of the data so that we can automate the application of all the pre-built algorithms that monitor and recognize issues before they happen, and also enable the operationalization of workflows. So if we're connecting to maintenance systems or if we are changing set points directly on the control system, we do that through the digital twin structure. So that's really important as well. It's not just for the analytics, but it's also how we operationalize the insights, and we do so at enterprise scale. So subject matter experts in this case are really empowered to force multiply their expertise across the enterprise and across all these assets. And the company achieved 92% margin based on this deployment. There are also some additional continuous innovation initiatives that are underway as a result of this. So there's new business opportunities as well. We're closing the loop between essentially data insights generated by TwinThread and the data centers. So we're connecting back to the assets. We're improving speed to service. We're optimizing energy usage, equipment maintenance, and other related processes. And this is a key part of the virtual center of excellence. It's built to drive best practices across the fleet. So Carl talked about that in the pyramid, the power of the fleet or the wisdom of the fleet. By capturing all of that expertise and codifying it in a platform and then deploying that expertise across the fleet in a scalable, automated way, helps to continuously drive innovation across the enterprise. So it's really important, and the digital twin structure is absolutely critical for that to happen.
So I know one question that probably our viewers have right now is going to be, you've talked about the importance of the digital twin, right? And being able to tie so much back to that. But how does someone who's brand new to this platform that might start with 50 machines, how do they start? How do they develop that digital twin? How does that get started?
Yeah, great question. So everything that I've talked about on the platform is meant for and built to empower the subject matter experts, the operators, the engineers, the technicians. In the case of factory use cases, the plant managers as well, the process engineers. So the system is built with a set of wizards that walk through certain steps in terms of how to configure a digital twin, as well as how to apply all the AI-enabled applications. And we do this in a no-code environment. So really, a subject matter expert takes their expertise of the type of equipment that they're managing or monitoring, and they're putting it into context. So automatically, we're bringing in time series data from IoT platforms or sensors. Time series data could represent pressure, temperature, things like that. And we're also bringing in event data from maintenance systems. We're bringing in from quality databases, custom built databases, anything that can help us understand that when an event happened, what were all the raw data sources from a time series perspective that informed or created that event. And that's key for all of the machine learning capabilities to work well. So you need a system that automatically puts all of that into context, so that we know that if we had a quality event or a downtime event, there were all these parameters beforehand that help us understand what happened. And then what we need to do in addition to that is understand the hierarchy of the asset. So what region is it in? What environment is it working on? What job is it doing? And in the case of factories, what production line is it on? When is it making product A? When is it making product B? When are there operational state changes? All of these things that help us structure the data in a way that gives us the raw material that we need to drive insights. All of that is automatically created in that digital twin structure. So as a subject matter expert, you know your assets, you know your processes, and the system enables you to take that knowledge, configure it in a no-code way, and then let the data also learn from how these assets and lines have been operating for a certain period of time, and that will start generating insights fairly quickly.
So I can say too that at least in the fluid power industry, one of the things that I get questions on a lot is, if I go out, if I put a digital twin onto a fleet of machines, right, what happens if I have a supplier that provides me product that's no longer up to spec? Something's wrong with that product. Maybe I received in 20 or 30 units of that product, and I start shipping machines. Maybe it doesn't pass my final inspection, but I get machines out there that now start acting a little bit different. What you're saying is, comparing it to that digital twin, we would be able to understand that sooner rather than at the point of failure of those machines, right? We would detect a difference.
Correct. Yes. And we're able to essentially substitute the quality lab results that has been captured 40 minutes after a production line in the case of factory scenarios, for example, and we're able to give real-time quality readings and be able to present the ideal startup conditions, for example, that you need to be running every time that you start up a line and you're making a specific product or you're running a specific asset. These are the parameters that need to be set in this way, and this to run these ideal conditions that are going to ensure that you don't have a negative event, whether it's downtime or quality in those examples.
That's awesome.
What I hear you saying, and what leaps out for me is digital twin up to the discussion we're having most often is a one-dimensional representation. It's like looking into a mirror. You can digitally represent RPM on a machine so that they're mirrored and you see what the RPM is. What you're talking about though is a multi-dimensional twin. You're talking about adding intelligence and learning and automation and so many other things that go with just that mirror that's created by the subject matter experts.
Right.
And I think
exactly.
that's important to say that it's not just
point.
a digital twin, it's a multi-dimensional twin.
Absolutely. That's a really good point. Great. So yeah, next slide here. I'm going to walk through an energy services example. So this example comes from a customer of ours, an energy services customer that manages a fleet of hydraulic fracturing pump trucks. And I'll walk through how we were able to flag for a catastrophic failure event using a combination of anomaly detection and predictive models that I mentioned are pre-built into the system as part of our asset-centric applications. And initially we noticed that there was an issue from an alert that was created at 5:49 Mountain Time, and it was automatically generated from an anomaly in the system. If we drill a little deeper, we see we've got alerts that show that there were 2 spikes that occurred before failure. And this is an important point here because a lot of times when we think about machine learning, we think about predictive analytics. And our applications are deploying both anomaly detection and predictive capabilities. So the anomaly detections are learning from patterns of behavior of specific assets and processes, and identifying what normal and not normal looks like. So when you're optimally running, what does that look like? And then automatically creating ways to alert technicians when there is high variability across any parameter that would potentially lead to a failure that we can also help to predict. So we're running both unsupervised and supervised learning models. The unsupervised learning represents the anomaly detection, as well as the supervised learning, which are examples of failures in the past. And one of the key points here is that with assets, you'll find that you may not have many examples of failures. So it's really hard to predict what a failure looks like if you don't have those examples. But if you're collecting a lot of data and you're bringing in data from Elevate, for example, we have, 5 to 10 years, 2 to 3 years worth of data. We're leveraging anomaly detection to be able to identify where's the variability? What actions do we need to take to eliminate that variability? And that results in ensuring that we're running our assets optimally, but also ensuring that we're not putting ourselves in situations where there are failures, both catastrophic or more technical failures as well that are just costly from an economic perspective. So that's a really key point here, is that both anomaly detection and predictive models are working automatically to support the optimal performance of a fleet.
And that's all in a no-code environment, right?
Correct. So what you'll notice here is examples of all of these parameters. In this case, we're looking at pump suction pressure, but we also had extreme variability across engine battery, turbo, transmission torque, engine turbo, things like that. So we're looking at hundreds of parameters across all these assets. So think about the level of scale required to be able to automate all of this machine learning across the fleet, but then ensure that we're driving anomaly detection at each different parameter that's important for generating variability. So and creating alerts. So in this case, you'll see that the adjacent startup conditions look very different. On the left, you'll notice that the conditions don't have a lot of variability. So the one that's highlighted here is the transmission torque converter temperature, and on the right you see that with that temperature reading, the variation is extremely high. And so we're talking about days before a catastrophic failure event, we're already identifying all this variability that's key for a subject matter expert to take action on and avoid any failures going forward. So the system is automatically doing this. Next slide. Thank you. Again, this is another view of other parameters here. These are more parameters that compare what normal looks like versus not normal. So the yellow highlighted regions are where variability is exhibited on these parameters, and this is what generates an alert. That alert then is surfaced up to a subject matter expert. That subject matter expert can automate workflows that take action to prevent any issue going forward, or to bring a parameter back to a normal state automatically. And there's different ways that we can do that. We can create a workflow that sends text messages or emails directly to a field service engineer to make a change. We can integrate with existing maintenance systems to kick off a work order and order parts ahead of time. Or in some cases, we can even close the loop and connect back to the PLC and make changes directly on the control system. So when I was talking about the journey to autonomous, if you think about all the automated steps that one can take based on all these insights that are generated by the system, these steps can be automated through workflows, and there are different ways of automating these workflows. You start automating those across the entire fleet, you're getting closer and closer to that autonomous services level, where you're seeing tremendous value in leveraging these technologies to solve all the potential challenges around asset health, asset performance, component failure, things like that.
Before you continue on with this, I think it's important to just pause for a second, because most of the industry is familiar with condition-based monitoring. That's not new. It's not new to try to set a parameter and monitor that parameter. But what you're saying is that there are times when you don't actually know what the
Right.
condition is that you need to be monitoring, which is why it's important to track all of these variables, and then the system will tell you what conditions that you need to monitor. And I'd say the next part to that is, a lot of people assume that we can only start doing this when the data is data forward. Like we can't look backwards at a data set and learn from it. But I
Right.
think TwinThread has the ability to attach to an IoT database and
Mhm.
look in the past to help us optimize the future.
Yeah, and the amount of computational firepower required to learn from 10 years of data or 5 years or 2 years um, historically to help identify learn from the data and determine what are the optimal settings that we should be running across all these parameters based on the job, that function that a specific asset is doing, the environment that the asset's working in, et cetera, et cetera. The system is learning what ideal looks like and what it should be, and then identifying going forward, applying anomaly detection to be able to flag variation that would deviate us from the ideal condition. And so all of that is taken care of, and we abstract many, many layers of, IT infrastructure, data lakes, connectivity, machine learning, automated data science to bring all of this key information to the person that knows the most about the asset or the production line and empower that individual to make those changes and move higher levels into that autonomous journey, where essentially you could have the top experts in the case of our data center solution example, I should say, monitoring thousands and thousands of assets, hundreds of thousands of predictive models automatically, hundreds of thousands of digital twins from the Center Virtual of Excellence, and driving those efficiencies automatically across the fleet. And that's where you see tremendous economic opportunity, both in the factory side of the customer type as well as the fleet or equipment services provider.
Yeah, just to kind of summarize it and connect the dots a little bit, one is that it will help you identify the conditions that you need to monitor. So that can be incredibly important in an R&D project that Viraj talked about when you don't necessarily know what you're looking for. Two, it can look behind you. So it can look at the data that's already been built, learn from that data to help understand and contextualize it. And three, and I don't think you've talked much about this, it's largely plug and play, Lewis. I mean, I've worked
Yeah.
with you on these projects. We're not talking hours and hours to get this
No.
up and running.
Correct. In a very, very short amount of time, incredibly quick time to value, for sure. Great.
Awesome.
So we'll skip to this pump RPM ratio. This is another view. So there are many different views within the system. I can click into a specific timeline for a parameter and see. This is an example of what I was mentioning in terms of the key inputs for a digital twin. In this case, you're seeing time series data, and then overlaid on top of it, you're seeing event data that we're getting, that's identifying when the asset is running or not running. So we can see everything, all of the conditions that occurred before a specific event. And we noticed that there were hard startups that occurred in two previous events that help inform what happened before a particular failure. So there's many ways of drilling into these visuals, and they're very advanced visual capabilities in TwinThread, but TwinThread is really meant to surface up the most important information that a subject matter expert needs to make a decision and to create a workflow. So they wouldn't necessarily look at this specific visual to make a decision. They would get the alert, and then they would look into that alert, and then they would apply a workflow But if they wanted to drill down deeper, these are the types of views that they'll see. So yeah, the next slide here shows another view of that as well.
That probably helps out quite a bit with warranty analysis too, wouldn't it? I mean, understanding what was leading up to, was there alerts that were happening, right? What was really going on with it? Was the end user doing something they shouldn't be doing with it?
Right, and we can track also the actions that were not taken when an anomaly was surfaced as well.
Good point.
Yeah. Yeah, we'll go to the next slide. Yeah, and so this is the view where the system prioritizes what are the top anomalies for the operators. This is an example of what I'm talking about. If I'm an operator and I don't necessarily have time to look at all the graphs and understand what happened beforehand, I can quickly see from the system what are the top priorities that I care about. And this is a view of that. Go to the next slide as well. Yeah, this is showing that there was a high suction pressure alarm as well. So there's many different ways for me to triage a potential failure event by looking at all the different data sources or different visuals and analysis tools we have in the system.
Well, and it's also an example that you mentioned early on, which is there's anomaly detection, so that's your unsupervised learning, and then there's supervised learning, which is sort of organizing it for you and letting you know what you need to pay attention to, which is essentially keeping it simple.
Yeah, correct, and predicting an event as well. So yeah, this slide here, here you can see the difference between normal conditions on the 20th and the high variation on the 21st, transition essentially. And these anomalies can kick off those automated workflows that are created and deployed and managed in our digital thread workflow environment. And that's what drives prevention well ahead of a failure event. So when I talked about the digital twin as well, digital twin not only creates the raw material for analytics, but it also is the engine that we use to operationalize actions based on these workflows that we create to prevent catastrophic failure events, as this example shows. So this is one of the many ways that the platform can operationalize these insights. Now, if you imagine running hundreds of thousands of models across thousands of parameters and hundreds of assets, that's a lot of work to build and maintain, and it's absolutely critical that we've considered scale from the very beginning. The ability to scale from 10 assets to 100,000 assets very quickly and automatically is key. So our platform would identify these patterns of behavior that require all the preventative actions well ahead of time to prevent a catastrophic failure event. This is just one of the many examples of that. The flexibility of the platform that I talked about earlier on can be demonstrated by the way that our partnership with Elevate and Applied comes together to create this virtual center of excellence that monitors thousands of pieces of equipment from a single platform to prevent these issues and to optimize performance. And essentially the way it works is data from the fleet are captured by Applied and Elevate, fed into twin threads, pre-built and scalable architecture that I talked about to really operationalize these preventative actions across the fleet. And the digital twins automatically contextualize the time series data, the event data in a enterprise-wide asset hierarchy that enables essentially subject matter experts to monitor all these capabilities at scale and create the insights from the applications that are driving all these machine learning capabilities in the background. And the digital threads are the logic, and it's the no-code workflow environment that applies the logic and the workflows that automate the actions from the insights and really allows us to execute on the results from all the machine learning applications that are deployed across the fleet. So each layer enables that key transition to autonomous services where there is the highest business value by operationalizing actions that drive efficiencies across the fleet. And we can do that at early on in the process. So when we contextualize data, we've configured the digital twins, and we've got the digital thread logic running on those twins. Even before we apply our first machine learning model, we can start operationalizing workflows that are helping to bring some of the equipment of the fleet into higher levels of operational efficiency, and we can do this by establishing KPIs. We can do this by creating alerts. There are many different ways that we can operationalize, so we can start seeing value very early on in the process of bringing all this together. So it's a really important partnership, and really shows how the flexibility of the platform supplements and leverages the IoT investments to drive value from achieving the autonomous service level.
Yeah, and I'll comment too. I think a lot of people that are watching, just so you guys know, we don't need to boil the ocean with this stuff right away. There are steps that we can take with this. Your IoT journey can go in phases. Oftentimes when we work with you guys one-on-one, it's, we're setting out a plan, we're setting out milestones and everything. We'll start with one pilot. We'll get, excuse me, we'll start getting data streaming. We'll start, validating that we're hitting the KPIs that you're asking about here too. So I know we covered a lot there. Here again, I wanted to make sure that in this webinar we covered really, what is the epitome of what you can really get to with all the IoT data. But please don't feel like it's any sort of an overwhelming process that has to be done immediately all in one shot. We can evolve this too, and we can work very closely with you guys as far as, what are your goals that you're trying to achieve with IoT? What is that big driver for you in your business, right? And Carl, I know you and we talk about this slide all the time, right? But maybe there's one KPI that's very important for you, or maybe it's controller flashing that's important for you, or maybe you want to figure out a way to support your dealer networks a little bit better. There's so many different things that I think IoT can provide here. And Louis, you did a great job at covering what can you really do once that data is in the platform. And I think that really, for me, the fact that you don't have to necessarily plan and say, okay, it's these sensors that I know are tied to this issue. I may not know what sensors they are, right? But the platform can help me see that kind of information. That's the kind of thing. That's kind of having, that subject matter expert in your back pocket that can really look at the data and say, you didn't look at this before. Let's look at something else, right? Let's look at an area we didn't think had anything to do with it, but with TwinThread, we could easily determine that.
Yeah, and I
So
think
much
it could
value
be
there.
a little, it certainly can feel a little overwhelming when if you're new to this, or if it's something that you're just on the initiative. But for me, from the way that I look at it is, I'm of that generation who was in a car, who used to have the Thomas guide and was trying to figure out the address, flipping through pages at night and trying to
Yeah.
figure out my paths, and then checking my book while I'm on the freeway. And if someone had come to me and said, "Hey,
Right.
I've got a phone. It's going to allow you to plug your address in. It's going to monitor your journey. It's going to tell you when to turn, where to turn, and all you have to do is set it up." I'm pretty sure at that point I would have said, "I kind of don't want to go slow. I'd like to go right there. I'd like to get
Right.
that now, because this is
Yep.
awful. I'm
Yep.
in the dark here." So it certainly can be a little overwhelming, but hopefully in this presentation you've learned there's a lot of people supporting you, a lot of partners that are very strong in what they do, and we would like to get you into a place where you're maximizing the return on your investment in IoT.
Yeah, and here at Applied Fluid Power, we definitely have IoT experts. Viraj and myself have obviously been involved with this for quite some time. We obviously partner with very great people here. Carl and Louis, appreciate your time. Thank you very much for helping to deliver this message. We encourage you guys to reach out. You can go to our website, which is appliedfluidpower.com. You'll see our whole IoT area there. There is a contact form that will be there as well. And at the end of this presentation too, there'll be some additional contact information that you can use to reach out to us. But we highly encourage you reach out to your local account manager, or send us that information in the contact form. But appreciate everyone's time today. I know this can seem like a lot, but here again, we can be very nimble with this, and we really feel like IoT is going to be, very soon it's going to be the standard in the fluid power industry, just like all the other initiatives that we've had that are now just the standard, right? And we're ready to help you on that IoT journey.
Thanks,
Appreciate
everyone.
it, guys. Thanks everyone for attending, and we'll catch you soon.